we were talking about the flux integral, and I already did one example using what I'm calling the general method. And here's the flux integral. Here's the general method for evaluating it. And by the way, in all of NMath A, I probably found this subject most difficult. At least in the textbooks I consulted, I was not happy with their treatment. It was confusing and kind of missing. So hopefully my approach is more clear. And again, if you want the more full story on it, email me and I'll send you my lecture notes. Because it's kind of a complicated subject. So I'll do another example using the general method. And then I'll talk about other methods, simplifying methods that you can use in certain circumstances. So recall this, if you want to call this a formula, this is the way you evaluate. You have to get everything in terms of U and V and then do all these operations. Let's do another example. Here's our vector field, and here's our surface. This thing in terms of x and y, where x and y are both positive, and then the z goes from 0 to h. You try to draw it, it might be something like this. This is, I believe, this is an ellipse in the xy plane. My scaling's kind of screwy here, but it, when y equals 0, it's just x squared equals 4 or x equals 2. X greater than 0. And when x equals 0, you get y equals 4. Something like that when you look down from the top, just strictly in the xy plane. So in this case, it's not parameterized for us. We have to come up with the parameterization. In the other example, it was a sphere or a part of the sphere, and we were already given a way to parameterize a sphere. So now we have to come up with it ourselves. And the z part's kind of taken care of. He's off on his own. But x and y are given in terms of each other. So we can use one of them to parameterize for both. I'll put x in terms of y. I'll move the y part to the right, 4 minus 4y squared, and then I'll take the square root of both sides. I can do it because everything's positive here. So I have x equals this expression. I now have x in terms of y. So now it's going to be parameterized in terms of y and z. Two parameters. And y will go from 0 to 1. Go from 0 to 8. So what is r? Wherever there was an x, we put in what it is in terms of y. Y is just y, and z is just. You don't have to call them u and v, just as long as we get it in terms of two parameters. What is f? Every place there's a y, we keep a y. Every place there's a z, we keep it a z. Every place there's an x, we use this function of y. Here we have our f. Now we have our r and our f in terms of the two parameters. Now we need to take those partials. R with respect to y. Here's r, take it with respect to y. This guy is going to be, 1/2 cancels the 2. 1 minus y squared to the minus 1/2 times minus 2y. Anyway, there's that term. Y with respect to y is just 1. Z with respect to y is 0. And with respect to z, no z here, 1. 0, 1. At the r sub y and the r sub z. Now let's cross them. In this case, it's kind of easy. We don't have to set up the determinant because it's a I thing crossed with a k thing and a j thing crossed with a k. I won't go through that, but that's that cross product. And we did y cross z. So this is always going to be 1 in the x direction and 0 in the z direction. And this guy is always going to be positive in the basically the y direction. So it's going to be out. It'll be kind of to the right, in the positive y direction here. That will be the convention for what positive flow means. Okay, the next step after we got this cross product is to take the dot product. Here was our f, here's our n. Dot them, simplify, you get this. And this becomes our integrand. Now we integrate over the two variables, y and z. Y will go from 0 to 1. It goes from 0 to h. And at this point, it's just normal calculus. Let me quickly go through two other methods that might be used. Let's go back to the original definition of a flux. What if the f dot n is a constant? Then you could pull it out. And if you know the area of the whole surface, you don't even have to take this integral if you already know the area. So the direct method says use the definition directly, and you don't really have to take any integrals. Trick to this method is to knowing whether it applies or not, and whether you do know the area of the surface. If you don't know the area of the surface, you still got to take this integral. How do you know f dot n is a constant? I gave tricks for knowing that in my class for exams, but that was kind of tailored to my class for exams. In general, you wouldn't know ahead of time. You might have to go through some trial and error. That's why I gave hints on my exams, so they wouldn't have to spend time doing trial and error in class, in the exam. Find the upward flux. This is the vector field. And the surface is just this horizontal disk. Look at this. This is a disk of radius 3 hovering parallel to the XY plane at a level where z equals 2. Just a flat circular disk as it's centered at 1, 3. Well, the n, remember that's the unit vector that's normal to the surface. Surface is flat like this guy is. That n is just in the positive or plus or minus k. We'll make it the positive k. So n is 0, 0, 1. Here's our f. What is f dot n? All that matters is this third component, which is z squared. And on that surface, z is a constant. So f dot n is the constant 4. We had to take this dot product to know that. So f dot n is just 4. We could bring it out of the integral. We're left with the surface area, and the area is a circle of radius 3. That's what we do, and we don't even have to take an integral. It's 36 pi. I think I'll get to this last simplifying method in yet another video, because I don't want these to go much longer than 10 minutes per video. So this will be the last easier method I'll use to do a flux integral when it applies. I'll talk about that next time.